to start class on time today. All right. Good afternoon, everybody.
Good afternoon.
Okay, so there was a request to talk real quick about memoryless and stable systems. Are there any other questions, comments, concerns? Before I make him put his phone away.
I don't know if I have an older version of the book, but there was like a sixth attribute in that version of the book. I can't remember the name of it.
What attribute was that?
I can't remember the name.
Yeah.
I didn't read it because I was like, oh, I don't notice that. I'm just gonna skip it.
Okay. I don't think it's important.
Yeah. It was like in between like causal and linear or something. It was like a sixth one.
Weird. Okay.
Yeah.
Strange.
Accumulator?
What's that?
The accumulator system?
Something like that.
Well, that was an accumulator was an example. I don't think it was like a system.
Oh, maybe.
Yeah, it was an example of a system. But anyway, let's real quick talk about the two we wanted to hit real fast are memoryless and stable. Memoryless and stable. Okay. On the first step, memoryless. Who remembers what memoryless means?
I don't think it depends on that specific.
Yeah, right. So the value, let me write it this way, the value of the output then only depends on x of n at the same value of n, right? So that means you get one sample in, you get one sample out, right? So for example, what did we have? We had like y of n is equal to x of n squared, right? Is this one memoryless? Yeah, right, nothing happens, right? It's just, you know, y of -2 is dependent on the square of x of -2, right? There's no additional symbols that are needed. What about, let's see, this other one, the one that's a logarithm, log base 10 of x of n. Is this memoryless? No, what do you mean no? See, it was a trick. You thought I was going to give you one that wasn't for the second one. But no, it is, right? It's still memoryless because it has, again, y of n is still only dependent on x of n at that value of n. Nothing changes, right? X of n isn't being shifted around anywhere, all right?
That one's not stable.
What's that?
That one's not stable.
It's not stable. We're going to come back to that.
Yeah, that's not stable.
Yeah.
If it had like x of n minus n naught though, would that be not memoryless?
Check this out, right? X of n, the delay system, the very first one we talked about,
Yeah.
we'll say n minus n naught. Is that one memoryless?
No.
No, right? Because the output n is dependent on an x of n that's getting shifted, right? So x of, if this case, if we said n naught was equal to 2, right? And we asked for x of, 3, we would actually get x of 3 minus 2 is equal to x of 1, right? Right. So since we asked for 3 and we got 1, not memoryless. So that's memoryless. Does that make sense?
Yeah.
Yeah. And then stable, basically just said,
It's bounded by.
yeah, if you, let me write it this way, you will get a bounded output if you have a bounded input. Right, what do we mean by bounded? It means finite, right? It means it's not going to infinity, right? So x of n is, or the absolute value of x of n is less than or equal to some bound on x, which itself is less than infinity, right? And the same thing for y. The absolute value of y is less than or equal to some bound, some finite bound of by, which itself is less than infinity, right? So if you give it a finite number, you're going to get a finite number out. So let's look at all these ones that we just did. Y of n equals x of n squared. Is this one stable?
Yes.
You bet, right? Now you might be sort of tempted to think it's not stable, right? Because the exponent makes it seem like it's going to like shoot up forever, right? But it's not going to shoot up to infinity, right? Even a huge number squared is still a huge finite number, right? So if you give it a finite number, you're going to get a finite number out. This one, though, the log base 10 of x of n is not stable. Because there you can show an example of if I give it a finite number, in this case if I say that x of n is equal to 0, which is bounded, it's a finite number, then y of n is equal to the log base 10 of 0, which is negative infinity, right? So this is an example, I gave it a bounded input and got an unbounded output, right? So the logarithm isn't stable.
So what if it has like x of n multiplied by something? Would that be unstable since you don't know what the variable would be?
So things like stability depend on the parameters, right? So I'm trying to think of a good example of this. So something like multiplication, right? If you had like, a times x of n, would probably still be stable, right? Because you're bounded, right? Finite x of n is going to get you a bounded output, right? You're not going to get infinity from the multiplication.
Yeah.
Well, actually, I can think of a counterexample right now. What about this? How about y of n equals x of n over some constant a? Is this stable?
Not stable if x of n equals 1 over n. Or no, if a is 0.
Right, if a is 0. But my point is, if a is not 0, then the system is stable. So just this definition alone doesn't tell us if it's stable or not. Does that make sense?
Yeah.
Right? It's only when you say, all right, we're going to pick a value for a, that will tell us if it's stable or not, right? If we pick 0, well, there's lots of reasons why it would be bad to pick 0, but you get the idea, right?
Yeah.
So the general expression in and of itself is not enough with regard to these other constants. Cool?
So the answer to that would be when a is not 0, it is stable?
Yeah. And when a is 0, then it's always equal to infinity, which is, technically not stable. It's not useful for anything else, but it's not stable. All right, memoryless and stability. We good? All right, everyone have a good time with that last homework assignment?
So if you can plug a value in and get a finite number back, it's stable.
Yeah, if you give it a finite number and you get a finite number back, it's stable. If you give it a finite number and you get an infinite number back, it's unstable. Now, if you give it an infinite number and get an infinite number back,
Could be stable.
it could still be stable, right? It's about, you gotta have the bounded input, right? Finite input gets us finite output. If you give it infinite input, then that doesn't tell you anything about stability. All right.
Professor, for the homework, should we always assume that the inputs are bounded? Does that help?
Yes.
For every problem I have to write, like bounded if the inputs are bounded if the inputs are.
Well, no, because that is the definition of stability, right? So you could say, by saying it is stable, you're already doing that, right? Since we've defined stability to be based on a bounded input. So you don't have to go out of
Okay, I see.
so you don't have to go out of your way to say bounded input.
Yeah.
Okay. Any other questions before we do today's lecture? I think we might get out a little early, but we'll see. So today's lecture is officially called LTI Systems. But as you will quickly see, it's not what this lecture is about. So, it's just what the title of the section. I think they titled the section this so they can like surprise you. Okay. So, what do we mean by LTI systems? So I'm going to say this: the vast majority, of the systems that we will deal with in this class, if not all of the systems that we deal with in this class, systems used in this class will be linear and time invariant. Linear and time invariant systems are so ubiquitous they get their own label. They're LTI systems, linear time invariant. So like I said, most, if not all, of the systems that we're going to look at from this point on to the end of the semester will be LTI systems, linear and time invariant. The reason for this is pretty much all the interesting things you can do, you do with LTI systems. I'm sure there are some spooky ways to use non-LTI systems, but that's outside the scope of this class. So the first thing I want to say is, remember on like the first or second day, we talked about the unit sample sequence, right? And what were some of the things we noted about the unit sample sequence?
N is an integer.
What's that?
N is an integer.
That n is an integer. The value of the sample sequence is what?
Also an integer? Or, no.
Continuous number?
No.
The output? Oh, the unit?
Delta n is equal to what?
0.
Oh,
And does not equal 0.
And
1 when n equals 0.
1 when n is equal to 0, right? And we also had this other sort of relationship that I said at the time was dumb, but it would come back around and be important. The one that was x of n is equal to what, k equals negative infinity. It's positive infinity of x of k times delta n minus k. Right? Remember we talked about this? And I said, wasn't it kind of silly to have a definition of x of n that still makes you know what x of n is? You don't get any new information from this? So I said it's a little bit redundant, but it's going to come back around. Well, it's back. So because of this relationship, and because of the fact that our systems are linear and time invariant, some cool things are true. We can say that, you know, if we start with this, that y of n is equal to, you know, t of x of n, right? Our definition of a discrete time system. And our discrete time system our x of n is equal to that guy. We say y of n is equal to t of the sequence k is equal to minus infinity, positive infinity, delta n minus k, right? Oh, forgot the important part. Stupid. X of k times delta n minus k. All right, so why is the fact that our system is linear helpful here, right? Because it's linear, what can we do?
Additive and scaling.
What's up?
The additive and scaling.
The additive and the scaling. Okay, what do you want to do with the additive and the scaling?
I don't know.
I don't know. So that's what I'm asking you to sort of guess, right?
Maybe
I'm saying this, we got this, and because y of n is linear, let's focus on the linear part first. Can we manipulate this in any way?
if we can make one of them a constant, we can pull it out.
What's that?
If we can find a constant, we'll be able to pull it out.
If we define a constant, we can pull one. If we define one of them as a constant, we can pull one out. All right, so how would we, you're on the right track. So how would we define one of them as a constant?
I would say that the impulse function, we're going to find some way of pulling
You want to pull the impulse function out. Okay, I like that. Who's got something else? We're on the right track, but we're missing some details. Saw you cramming in the textbook before class, man. What do we? You're not gonna get that far.
Anything.
What makes it a constant? What makes a constant in an expression?
That it's not changing, it's not varying.
It's not varying.
It's not dependent.
You guys are taking Cal 2, right? Let's take an aside for just a moment. Cal 2 does. Are you guys in Cal 3? Have you guys taken Cal 3?
Yeah.
Okay, all right. So multivariable integrals is a thing that everyone's familiar with, right? So if I have, well, just one integral, and let's say that I've got a function with respect to x, a function with respect to y, and I'm doing my integral with respect to x. How can I simplify this before doing the integration?
Pull G of Y out.
Why pull the g of y out?
Because it's not dependent on the variable.
Because it's not dependent on the variable we care about, right? This is the cool part. So yeah, so we could take this and we could say, well, g of y, since we don't care about y, since we're only integrating with respect to x, we can just say, get rid of there. This is now a constant in the universe of our integration. And now we're just doing f of x dx. All right. Take that concept, apply it to our discrete time system. What is the independent variable? What is the thing that we care about? It's n, right? Because y is dependent on n, right? It's y of n. So, what can we remove?
The input signal.
What's up? The input signal, right? Because x is only dependent on k, and we only really care about n, the x is out, right? So I can take this and I can rewrite it as y of n, and I can bring out that sigma. I can say y of n is equal to, actually, do I want to do that? Yeah, I do. Okay. Is equal to k, because we got to have a definition for k, so k is equal to negative infinity to plus infinity of x of k times, like that, t of delta n minus k. Yeah? All right. So I can pull that x of k out, and only now just be multiplying our input signal, our input samples, by this transfer function on just the input sample sequence. Right? It's getting a little weird, right? So we can simplify this expression a little bit. By the way, we call this, have you guys talked about this in your linear systems class yet?
Superposition.
Is it convolution?
It's not convolution, it's not superposition. Although it's about to become both of those things in just a moment. But what do we call?
Oh, the response?
Yeah, the something response.
The input response?
Not the input response. You got most of the syllables right there.
The output response.
Not the output response. What do you guys call the delta
Sample
function?
response?
What?
No.
What do you guys call the delta function in your linear systems class?
Direct delta.
There's another name. Starts with an M. Starts with an IM. Fine.
Impulse?
You guys are no fun. Thank you. The impulse function. Yeah. Right? This is called the impulse response. Of our system. So because that's the impulse response, what we're going to do is we're going to take it and we're just going to make it its own function because we're lazy. We don't want to write that much. We're going to say y of n is equal to sigma k is equal to negative infinity to positive infinity of x, not k of x, x of k, times h of n. Where h of n is the impulse response of our system, and it's equal to all that stuff from before. It's equal to the transfer function acted upon delta n minus k. Okay, so any questions about how we got here? No, it's relatively straightforward, right? Once we got that business of what variable matters out of the way. Okay, so this guy has a name that I once heard Dr. Saraf say exists only to scare undergraduate students. What is this?
Is it convolution?
It is convolution, yeah. Right? And if you guys have talked about convolution in your linear systems class and you look at the example before we converted it to H, you can kind of see it, right? Like it's kind of in there. It looks a little bit similar, right? If you sort of stretch the sigma out to an integral and you replace the k with a tau, right? You would get basically your continuous convolution, right? So this is our discrete convolution. And for what it's worth, it's a lot easier than its continuous counterpart. Oh, actually, I'm not quite done. I forgot one step. That was the linear part. The time invariance gives us an extra bit. It's not yet. It's not convolution yet. I lied. Spoiler.
I think I can.
What is it?
That we can make it y of, oh no, I was gonna say y of n minus k, and then it'll just be the same on, but yeah, never mind.
All right.
No.
Not an integral, right? Since we're using discrete values, right? The sigma is the integral in discrete terms, right? It's the same thing. That's why it even kind of looks like it. The integral is just a sigma that they like stretched out to make it continuous. But anyway, because it is time invariant, right? We can, as long as we don't mess with n, everything else can be messed around with. So we're going to say x of k times h of n minus k. That's the part I forgot. Now it looks like convolution. You know, the integral of what f of x times, or x of tau times something of x minus tau. All right, that's our convolution. We call it the convolution sum, which really should be the title of this lecture.
Just a quick question.
What's up?
So in linear systems, we subtracted it from tau, but this one we subtracted it from k, right?
Mm-hmm.
So k is a constant. It's not.
K is a constant, yeah.
Okay.
What we're going to do is, and we're going to, the only thing I have left for us today is we're going to work one out by hand. We're just going to draw it out and see what it looks like when we take, you know, H and just sort of shift it over.
That's the only way you have to do it.
It's the only way to do it, man. Yeah, I agree. So that's what we're going to do. Okay. And we're going to simplify that process a little bit too. But yeah, so in the same way, K is like the tau in your continuous convolution, right? It's where the tau is how you shift it continuously. The K is how we click it along on the samples. All right. And last, before we do that example, the shorthand, same as your linear systems class, I think. It's been a little while since I took that class, or done continuous anything. Right, x of n convolved with h of n. So those guys are equivalent to each other. So that's the shorthand for convolution. Yeah?
Is there a difference between like an H and a U? Or...
Yes, the U is the unit step sequence, right? Which is its own special thing.
People like interchange like the H and the U before.
There are a lot of applications in which using the step sequence or the step function as your impulse response has useful properties. There are reasons to do that. And so what they're doing is they're treating the unit step sequence or the unit step function as the impulse response.
Okay.
And then doing the convolution, right? But in general terms, it's H.
Okay.
Okay, because you can convolve anything with anything else, right? It doesn't have to be an impulse response. All right, let's work one out. So let's say that we've got a function, or excuse me, a sequence. So 0, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, -1, -2, -3. And let's say that at -2, so this is our, so that's n, this is our x of n. And let's say that at -2, we have 1. At 0, we have 2. And at 3, we have -1, right? Just a couple samples. Really simple, arbitrary sequence. And let's make our impulse response sequence this. 2, 3, 4, 1, 2, 3, 4, 0, 1, 2, 3, 4, -1, -2, -3, -4. And we'll make at 0, make it 3, 2, and 1. Right. This is our h of n. Okay. So all we're going to do is we're going to find y of n by convolving x of n with our input h of n. Now, this is basically the rest of the class. The rest of the class after this is just like finding interesting ways to come up with h of n to do interesting things, right? But at the end of the day, you're going to get an h of n, you're going to convolve it with x of n, right? A filter is basically just that. You take some sequence and you sort of slap it over your input samples with convolution, and now you have a filtered signal that came out the other side. Okay, so what's going to happen is, right, we're going to take h of n and we're just going to essentially slide it along x of n, sort of multiplying and adding all the rest of the way. Now, we can make things a little bit simpler by taking advantage of superposition, right? What was superposition?
That we can add two signals that are running through a system together, and it's the same as we can run them individually and then add their output, and it's the same as running them through the system together and then just having that output.
Exactly, yeah. Right? So instead of doing it all at once, we can break it up into pieces. So what we're going to do is, instead of convolving our signal with the whole thing, we're just going to see what happens when we attach it to just each of our samples, our x samples individually. And then we can add them up at the end, and that's our solution. So the first thing we're going to do is just look at, come on, -2, right? We'll pretend that's the only thing that happened. So we'll say that, bless you, x of -2 of n is equal to x of -2 times the delta of n plus 2. All right, so we've isolated just the sample at -2. Well, this means that our y of n, and here's the important part, is going to be equal to x of -2 times h of n plus 2. So we're going to take h and we're going to shift it over and stick it right on top of our first sample. Does everyone understand that part? That is the most, if you get that part, everything else is easy. Everyone understands what we're doing? Okay. And what that means is y of n, so x of -2 is equal to what? Just 1 times h of n shifted to the left by 2. Or yeah, shifted to the left by 2. So what we're going to do is draw what that looks like. So 0, 1, 2, 3, 4, -1, -2, -3, -4. I can label those because they don't matter. Okay, so h of n starts at 0, we shifted it to the left 2, and we multiplied it by 1. So that means our, I should have labeled that, y of -2n means we're going to get this. At -2, we'll have our 3, then a -1, over 2, and then at 0 we have our 1. All right. So this is what you get when you convolve our impulse response with just that one symbol.
So h of n plus 2 is, you know, it was like in our derivation, it was the impulse, the unit impulse. In this case, it's where did we get that graph on the top? Like, was it given?
Which graph?
H of n?
Yeah, I made it up.
Okay, that's given.
Yeah, that's given. Yeah, the x of n and the h of n are given to us. We got to find the y of n's. Okay. Any other questions about this step? All right. So we're just going to do that for every sample and then add it up. So the next one is at 0. So we'll say that we just want to isolate x of 0 at n, and that's equal to x of 0 times the delta function that samples at n plus 0, meaning that y of 0 of n is equal to x of 0 times h of n plus 0. X of 0 was equal to 2. So y of 0 of n is equal to 2 times n plus 0 is just n. So it's not shifted at all, but it is multiplied by 2. All right, so that means that our new graph looks like this: 0, 1, 2, 3, -1, -2, -3. So we had 3, 2, 1 starting at 0, so that means we're going to have what?
6.
Yeah, good.
4 and 2.
Yeah, we're going to have 6, 4, and 2 for our y of 0 at n. Okay, next step. The last one, there's only 3 samples here, is at 3 we have -1. Bless you. So let's see, so we want to know x -3 of n is equal to x of, not -3, +3. X of 3 sampled at n -3, which means that our y of 3 of n is equal to x of 3 times h of n -3. Now x of 3 is equal to what? -1. So that means we're going to have -1 times h of n -3. So that means our impulse response h of n is going to be shifted over 3 and then multiplied by -1, so it's going to be flipped over. So 3, 4, 5. 0 over here. 0, 2, 3, 4, 5. So that means at 3 we had -3, -2, and -1. Cool.
Professor?
Yeah.
So the left-hand side there is just the input multiplied by the unit impulse, which, why exactly do we need that unit impulse there?
Why do we need that? We don't really need it. It's more just like a mathematical kind of formality. But what we're saying there is we're defining what our x of 3 is. And our x of 3 is x at 3 by sampling it using the sample sequence. Right? It's like I said, you don't really need it in order to like solve the problem. It's just sort of, like I said, a mathematical formality.
And we're not plugging in x of 3, right? Or x3 of n. We're plugging in x3.
Yeah, x at 3. Yeah. So whatever that is. In this case, it was -1, right? X of 0 is 2.
But we could plug in x3 of n, right? Like, would it make any difference for our y calculation? Oh no, it would, because it would take everything else and make it 0.
Yeah.
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 Got it.
Because the next step, so superposition says, right, we could take them all and treat them separately, which is what we've done. So what's the last step? We got to stick them all together. Actually, I don't want more room than that. So now, come on, now. Now you come back. just as bad. Okay. And let's see, we have 0, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. And this is going to be our y of n, which is equal to that y, -2 of n, plus y, 0 of n, plus y, 3 of n. Stop that. Okay. So we go and add them. And what was the leftmost thing we had was at -2. So at -2 we had 3, and then at -1 we had 2. So those are largely unchanged. So we had 3, we had 2, and then at 0 we had some overlap, right? X -2 had a 1 at 0, and x of 0 had a 6 at 0. So what does our final result have at 0? 7. Oh wait, did I do this wrong? Hold on. Oh, because I screwed this up. I should have started at -2. Three, 2, and then at 0.
7.
Bam. 7. All right, and then at 1, so 1 and 2 only occur in x sub 0. And that was 4 and 2. Bless you. And then 2. And then finally, for x of 3, we had 3, 4, 5 at -3, -2, and -1. -3, -2, and -1. So there we go. That's our y of n, which equals x of n convolved with h of n. And there we go.
Can we see the originals next door?
Right, these guys? So you can kind of see it, right? If you look at what our h of n was and then what our x of n was, it was like 1, then 2, then minus 1. And then you look at the shape of h of n, you know, that diagonal 3, 2, 1. Like you can kind of see it, right? You see where it starts 3, 2, and then it gets big, but still diagonal, and then it flips over, right? You can kind of recognize the patterns in the resulting signal.
Looking
Cool.
at it like that, though, weirder.
What's that?
Like if we were imagining that x of n was the impulse,
Mm-hmm.
then I guess then like imagining it is a little weirder.
Like if x of n was the,
Impulse, like look, go up.
like if you flipped it over?
Yeah, like if we were saying that the left one,
Yeah.
you know what I mean?
Yeah, you could do it though. I mean,
Yeah.
you still just kind of, it's still be multiplying and shifting the whole way down. So yeah, so you just isolate each one, shift your impulse response over, do it for each one, add them up at the end. That's your result. Any questions about how to do that convolution by hand? Cool. Well, that's good because that's your homework for Friday. I've created basically the exact same thing we just did, just a different sequence and a different impulse response. And I think this would be a fantastic next Python project. Write a function that does the convolution and shows us the graphs. So
That'd be useful.
I think that, yeah, and I think that'll be useful down the road too. So that's, you can count on that being the Python project that gets assigned on Friday is going to be doing this convolution in code. So you can just, you know, give it x, give it h, it returns y, and then graphs it. Cool. All right. That's actually all I've got planned for you guys today. We're about, what, 7 minutes early, which is fantastic. Any other questions, comments, concerns? Yes, sir.
Those are in the textbook. There's this one part that I don't quite follow. So it's saying, so that last sentence, it says when n equals 2, that x of n equals, that's, we can't assume that from here, right? Like that's given.
We bought one of the kits here with the case and a bunch of stuff.
It's basically just a constant.
No, I don't think so. I don't know what it means by when m is equal to 2, x is equal to delta.
Like that's given, right? Like that's like.
Yeah, that's given.
Like, hey,
That's given. He's
this.
telling you what it is.
Okay.
Yeah, okay, yeah. It's not derived.
Okay, because I was like looking at that and I was like, has to be given, right? But,
Yeah.
Okay.
Cool. All right. Any other questions, comments, concerns? Yes, ma'am.
Are we gonna go over problems at 2 at all?
I wasn't planning on it. We can at the, if you remind me, I'll do it at the start of class next time. Okay?
We bought one.
All right. Cool. All right. If nothing else, thank you guys. Y'all free to go. Yeah, look at that. Right on time.
So there was, they had a few of them that were already in the
Thank you, Professor.
project.
Thank you.
Check them out.